Datasheets are used by myself and electronic engineers pretty much every single day and multiple times a day. They form a core part of the work and are very important to understand. This is because datasheets help in choosing parts, for example, choosing passive components, choosing integrated circuits, diodes, and so on. They help with sizing those parts, tell you how they work. Datasheets will tell you about ratings, timings, bus specifications, seeing what external components you might need to interface this with the rest of your hardware design. Datasheets will tell you about mechanical aspects and are also helpful for firmware in certain cases, for example, telling you about register maps, which will help you write drivers and so on. Therefore, in this video, we will examine the core parts of datasheets, going through them together for electronic components, and see what similarities exist between most datasheets, and of course, where there might be some differences. Now, of course, it's hard to generalize as datasheets can and will differ between one another, but I'll show you what to look for in datasheets and how to use that information in your hardware designs. This, of course, can be a slight bit daunting if you haven't done this before or if you're a beginner, but we'll go through step by step together. To illustrate, I'd like to go through 3 different datasheets, again showing similarities and differences and what I would look for when I'm going through a datasheet. For example, we will look at this AP62250, which is by Diodes Inc., which is a synchronous buck converter IC. We will look at this CC1100 by Texas Instruments, which is an IF transceiver. And we will look at this MPR series pressure sensor by Honeywell. Now, I've chose these datasheets fairly at random just to show you that there are similarities between these and what I would then look for. A huge thank you to Altium for sponsoring this video. Make sure to check out the link in the description below or go to altium.com/YT/Phil's Lab and you can get yourself an Altium Designer free trial as well as 25% off your first license purchase, and you can check out all the cool features including Altium 365. Please visit the link in the description below to learn more about Altium 365 and many of the core features such as ECAD, MCAD integration, library management, design reviews and markups, and much, much more. Octopart is also a part of the Altium ecosystem, so make sure to go to octopart.com, which allows you to search for millions of components across hundreds of component distributors very easily. The first step that even comes before looking at datasheets in my eyes is typically narrowing down what parts might even be suitable. And for this, you can go to manufacturers' websites such as Analog Devices, Texas Instruments, and so on, if you have a vague idea of what part you need, or you can go to your preferred distributor or sites such as Octopart. For example, if I'm looking for a voltage regulator, a switching converter, for example, a step-down converter, I might start here and then hone in on the datasheets. So for example, on Octopart, I've got my voltage regulators open. I can choose, for example, what the maximum output voltage should be. So at least 12 volts, for example. I can say that I would want one output, an output current of 3 amps, and maybe a certain switching frequency. And this would already narrow down quite a lot of the parts that might be suitable and that might be currently available. So this, nicely enough, of course, also shows availability and can also show availability trends. Once you've narrowed this down using, for example, a distributor part search or a manufacturer part search, you can then click on one of these datasheet buttons, and Octopart, Mouse, or DigiKey will all have this. So if you've identified a suitable part, you like the price, and you like the basic specs that you set out with these filters, you can click on Datasheet, and this will then load the datasheet for you. So this is how I would typically start if my goal was, for example, to narrow down and select an initial batch of components that might be suitable for my design. Now, once you've narrowed down parts, then of course you come to the datasheet, and this is where this video, so to speak, kicks in. Let's examine these 3 datasheets we saw at the introduction and see what similarities there are and what I would look at and look for and how a datasheet is typically structured. The first thing being with the overview page. The overview page is for the manufacturer of that part to tell you need to know to make a somewhat informed decision if this part might be suitable for you. For example, for this AP6250 synchronous buck converter, we immediately see at the top, the input range is 4.2 volts to 18 volts. It can deliver an output current up to 2.5 amps. It's available in these 2 standard packages, so SOT563 and TSOT26. It has this certain pin out, and it gives you a description. It integrates 2 MOSFETs as it's synchronous, it's apparently high efficiency, and tells you a bit about how it works. Then there's typically an application section, so what this IC might be used for example, FPGA, DSP, and ASIC supplies, and then also a very condensed list of the main features. So an input voltage range, an output voltage range, maximum output current, switching frequency, quiescent current, and what kind of protection circuitry this might contain. So if you're looking at, for example, buck converters, you might have several of these datasheets open, and at a quick glance on the first page, you can quickly discern which ones might be somewhat suitable, and then hone in, as we'll see later on. Similarly, for this Texas Instruments RF transceiver, the first page is very, very similar. It'll tell us what applications this might be used for example, ultra-low power wireless applications, sensor networks, and so on, and give you a brief product descriptions. For example, what frequency bands this might work in. We already have a hint of what this package might look like, this QFN style package. And on the second page, so you might have to scroll down 1 or 2 pages to get the overall features, you can see the key features of this device. Again, package type, power consumption this might be, what additional features and performances it nominally has. Again, a good indication just to see if this part might be suitable for your particular design. Thirdly, this sensor, so again this Honeywell MPR pressure sensor, first page will tell you most of what you need to know. Now these datasheets of course look a bit different in the way they're designed, but the basic principle is that first page is an overall view. For example, here we have a certain package. You can measure pressures between these ranges. It has an I2C or SPI interface with 24 bits of precision, and so on. Fairly near the top of a datasheet are then ratings of the device. So this will be absolute maximum ratings as well as recommended operating conditions. As these names suggest, absolute maximum ratings is where the device will be damaged and best case it will have a reduced lifespan, and you really should stay away from these maximum ratings. For our buck converter example, we can go up to 20 volts DC at our input voltage pin, and then a different pin, for example our switch node pin, might have a different absolute maximum and absolute minimum rating. And this is what you can take from this diagram. We can also see that there is some sort of ESD protection integrated into this device, and it's rated up to certain levels given certain models. Further down, and this is what you typically should be looking at more because you want to stay in these operating conditions for this device, are the recommended operating conditions. So our supply voltage at input node should only be between 4.2 and 18 volts, the output node like so, and you should stay within these certain temperatures. Similarly, for our RF transceiver, we also have an absolute maximum rating section and a recommended operating conditions section close to the top of the datasheet. And of course, similarly for our pressure sensor, near the top of the datasheet, we have our ratings section. Again, absolute maximum ratings, for example, ESD, shock ratings, and so on, and recommended operating conditions. In addition to recommended ratings, you will also have an electrical characteristics section near the top of the datasheet. And this will tell you in rather a bit more detail about some additional parameters of the device. For example, for a switching regulator, we might need a feedback voltage to set the output voltage, and here we can see a range of that feedback voltage pin. So for example, from tables like these, you can get worst case scenarios and, for example, logic levels, for example, for turning this device on or off. Similarly, for the RF transceiver, we of course have the general electrical characteristics, for example, the current consumptions, and for example, different operating frequencies, temperatures versus current, and so on. And similarly, of course, again, for the pressure sensor, this will typically be near the top of the datasheet. Again, it's important to keep in mind that datasheets are different, the way manufacturers organize their datasheets are different, but what's important to know is that these sections should be, and in 99% of cases, are in the datasheet. For example, next would be the pin descriptions, and this is incredibly important, for example, when you're creating your schematic symbols in your ECAD tool of choice. It'll tell you the pin name, it'll tell you the pin number, for example, depending on package, and also a functional description of that specific pin. So for the buck converter, we have the input voltage pin. Let's say we're using a SOT563 package, that would be pin 1. So that would move that over to my ECAD tool, be that Altium Designer, KiCad, or whatever, and label that then as a power pin. Similarly for the enable pin, that's pin 5, and that I would select then to be an input pin. And this is how I can create my schematic symbols. Typically accompanying that, you might get a top-down view of the package or some sort of functional block diagram where the pins are labeled, and you might get to see the guts, so to speak, of your part. For the RF transceiver, here's an example what it would typically look like. You have this top-down view where you see the pin name, the pin number, and the view of the footprint as a very, very basic, of course, not to scale drawing. Accompanying that would then be, as we saw previously, a table, so pin number, pin name, pin type, and description. And this information you would carry over again to your ECAD tool. Same thing again for the pressure sensor. We have a view of the package, pad number, name, and description. If you'd like to learn more about symbol and footprint creation, I have videos on Altium Designer and KiCad on my channel, so make sure to check them out, how to transfer that data from a datasheet into your ECAD tool of choice. Another very important aspect of datasheets is a typical application circuit, and this would be a bare bones circuit that you, for the most part, can carry over to your hardware design. Of course, you'll probably have to adjust values, and this won't be a one-case-fits-all design, but this is a great starting point typically that the manufacturer recommends, and also it's a great way to see how many external components you might need to fit this into your hardware design. For example, when I'm choosing a buck converter and I have a rather small space constraint, I might prefer a buck converter that doesn't need very many external components, such as this one. This application circuit will also give you rough values for external circuitry, so it lets you see orders of magnitude of the components you might need. Again, a great indication if this might fit with your design, if you can maybe use similar component values and sizes and do bill of materials consolidation. Keep in mind, we'll come to a section later that lets us actually calculate and how we can calculate these component values. Same thing for the RF transceiver. We will have typical application circuits. For example, at the top, we can see a circuit which is for operating frequency of 470 MHz and at the bottom for 950 MHz. Now, these are two different circuits. They'll need different component values, but it shows you and gives you a good starting point of how to integrate this into your design. In this case, the component values are generic because, of course, it depends on your operating frequency, the type of matching, and so on. But it'll tell you about decoupling capacitors, which pads need to be tied to ground or to power, and what power, and so on. Same thing for the pressure sensor. We can run this pressure sensor either as an I2C circuit or as an SPI circuit. So nicely enough, we can see what decoupling capacitors we might need, what external circuitry we might need, and that these pins are multifunctional, so they could either be an I2C connection or an SPI connection. And that's exactly the process you would then use to implement that in your own designs. For example, I have a DAC here, and all of these decoupling and bypass capacitors and where I connected these voltages to are from the sections we saw previously. Also, how I created the symbol. I took the pin outs with the pin numbers and assigned them specific functions, all from the datasheet, all from the information we just saw. Nothing here I put in is particularly original, it's all taken from the datasheet. For components such as switching regulators, you might have to do a bit more work. For example, this switching regulator here, it has standard structures around it, such as bootstrap capacitors, output inductors, feedback networks, input-output capacitors, and so on. But these values have to be sized depending on the application. So I didn't pull these values just straight from the datasheet application schematic or out of thin air. You can either follow calculations from experience or from the datasheet. So for example, for our switching regulator, and typically in datasheets, you will have an application information section somewhere around the middle of a datasheet. This will give you various formulas in the case of power converters, how to size the components. For example, how to set the soft start time depending on which external value of capacitor you choose. Or if you want undervoltage lockout, it'll tell you how to choose values of R3 and R4 for the enable pin of this regulator. All equations should be given in the datasheet. Similarly, again for the RF transceiver, we have an application information or application circuit section of the datasheet. This will tell you what components there are, how these components might function, and how to select them. For example, here how to choose the crystal, how the components interact with each other, what decoupling capacitors you might need, and so on. For sensors, such as these very simple pressure sensors, usually you can take the information directly from the application circuit diagram, and there isn't usually much more around it. You have typical values for decoupling and bypass capacitors, the usual pull-up resistors for your I2C buses, and sometimes some external components that you need to add in. Again, all of this information you can take from the datasheet. There will of course be some further explanations of, for example, how the circuit functions, how external components are chosen. For example, in the case of pull-up resistors on an I2C line, you'll of course have to change the values depending on the bus loading, the speeds you want to achieve, and so on, but all this is typically given in the datasheet. Unfortunately, not always it's given in the datasheet, and you have to dive a bit deeper, and this is where application notes come in. For example, for ST microelectronics, when you're using one of the microcontrollers, the datasheet might be enough, but typically it's good to look for application notes, for example, notes on actual hardware development. It's laid out somewhat similar to a datasheet where you have specific sections depending on what circuitry you're looking at, but this will tell you, for example, what decoupling capacitors, bypass capacitors you need, what power rails you need, and so on. So oftentimes you might need to go the step further, go to the manufacturer's website and look up their application notes. But typically the datasheets should also advise you to look for those as well. A very important part, especially if you're handling PCB design as well or mechanics, is near the bottom of datasheets are packaged drawings as well as oftentimes recommended footprints. For For example, for this buck converter, we can see we have either the SOT563 package or the TSOT26 package. It'll give you all the standardized dimensions, so lead widths, package dimensions, heights, and so on. And typically they will have these standardized tables, as you can see on the right-hand side. Unfortunately, there isn't a very standard way of presenting this, or at least datasheets don't make the effort to present this in a standardized way. So sometimes there might be some missing information, or you might have to do additional calculations to get these dimensions. Oftentimes, there's also a suggested footprint or pad layout, so the schematic symbol, of course, in your ECAD tool needs to have an accompanying footprint for the actual physical part on the PCB. Now, this is not always included, and sometimes you might have to look up, for example, SOT563 recommended footprint or go via IPC guidelines. But this will then let you create footprints. Same thing for the RF transceiver. Again, we have a QFN20 package, and it'll give you recommended footprint dimensions. And same thing for our pressure sensor. We can see in the mechanical design of this part, but also the recommended PCB pad layout. Again, please refer to the videos on my YouTube channel, which tell you how to create your own footprints in Altium Designer and KiCad to see how you can get from these datasheet drawings into your ECAD tool and onto your PCB. Once you have your part on your schematic and the footprint as well, and later on when you come to the PCB layout and PCB routing, the datasheets will often also have a PCB layout section, which might serve as somewhat as a starting point of how to place your component and how to place the external components the centerpiece, so to speak, requires. Now, these PCB layout recommendations should be taken with a slight pinch of salt because these are written by application engineers who might not be PCB designers or follow PCB design best practices, but they might give you a good starting point as a recommendation. Same thing for the RF transceiver, so you have a section on PCB layout recommendations, but maybe not an actual image or surrounding circuitry that goes with it, so you should rely on PCB best practices. Or look up, for example, their reference design boards. Typically, manufacturers will create their own reference design boards. Again, look at them somewhat critically. They might not always follow best practices, but they might give you a good starting point of how to lay out your components and what components they chose for a specific part. For components such as these very simple sensors that have very basic interfaces, don't have particularly stringent power requirements, if you go to the table of contents, you won't typically see PCB layout recommendations other than just a recommended footprint. That's because there isn't too much to these particular sensors, and it depends on the mechanics and the fit of your design in any case. Another big part of datasheets is not just to help you with the hardware, but also with the firmware implementation. Of course, this depends on the device, but for example, for a microcontroller or sensors such as this, which has digital interfaces such as I2C and SPI, once you have the hardware in place, of course, you're going to have to make this work, so to speak, with a microcontroller, processor, and so on. And these datasheets will help you do that. Not only will they tell you how to hook up the communication channels, but they will also tell you about, for example, register contents. So this will typically be near the middle or end of a datasheet. For example, it'll tell you about certain registers. For example, it'll tell you what the sensor addresses are. For example, the default in this case might be hex 18, which might be good to indicate on your schematic diagram for your firmware engineer to then take over. It'll tell you how to read out the pressure readings, what, for example, a status byte means, and what the bits in that status byte mean. So very, very helpful for firmware. They'll show you timing diagrams, so it'll tell the firmware engineer how quick they can maybe run their clock frequencies at, what timing margins they have, and so on. And this is very nice. In this specific example, they might give you reference code directly in the datasheet. So you can take this code, port that over to your platform, and you have a good starting point, for example, to read out the basic pressure or temperature or whatever your sensor does. If it's not contained in the datasheet, your manufacturer oftentimes will be able to provide you some sample code. They might have some sample code on their website, or you can look for an open source driver. But this is a very nice part of datasheets and incredibly helpful, not just for hardware. Make sure also to check out the How to Write a Driver video on my channel, which is video number 30, which goes through exactly that process of going from a datasheet for an accelerometer, which I've mounted on a custom PCB, and then programming a driver in C that interfaces with this peripheral from a microcontroller. Keep in mind, we've just looked at the very basics and essentials of the main parts, for example, I would look at in a datasheet. If you require more information, of course, there are typically more sections in the datasheets that you can dive deeper into. For example, for this buck converter, there are efficiency graphs, for example, the output current versus efficiency at different voltage levels. There are sections, for example, on thermal resistance, if you're calculating, for example, power losses and then want to infer what the component might heat up to and what the board might heat up to in that specific area, you can use these thermal resistance values. Then there might be more performance characteristics, so various graphs, so for example, output voltage versus input voltage, load regulation in this case, and loads of extra information you can use to make better and better decisions and more informed decisions when you're designing with this part. Datasheets will of course also tell you if relevant interfaces are there about timing of the device, for example setup and hold times, timing periods, for example rising and fall times and so on. All the information also contained in datasheets, which can help you make informed decisions and help you with simulations, how long for example your traces are allowed to be and so on. Also for simple interfaces such as SPI or I2S and so on, you'll see how the interface typically works, what lines there are, and the relevant timing parameters of that device and of that bus. Additionally, what might be important is near the end of a datasheet is order information or how, for example, the package code is made up. Same thing for more involved parts. If we look at the table of contents for our RF transceiver example, there is much more information we can look at and find out, which lets us go into far, far greater detail. A datasheet in addition with application notes should be everything you need to incorporate this part into your design. Once you've understood datasheets and how to navigate them, how to make informed decisions, and how to choose parts based on datasheets, typical hardware designs can be a lot less daunting because all the information you can find in datasheets and app notes. For example, for a latest hardware design of mine, all these parts you see here, for example this USB-C power delivery controller, all of these external parts are chosen based on datasheets. Of course, there's stuff such as bill of materials consolidation, optimization, and of course making it more appropriate for your specific situation. But the basic outlines, for example for this PD controller, these buck converters, regulators, or even maybe more complicated components such as this gigabit Ethernet physical layer, all of this is based on datasheets to start with. So it really pays off to learn how to navigate these documents. Thank you very much for watching. I hope this video gave you a basic and good overview of what's in a datasheet and what to look out for, and how you can use that in your hardware designs. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest video. Thanks again for watching, and I hope to see you in the next video. Bye bye.